We have seen how to solve a set of linear equations using matrix inversion or by using elimination techniques. So, now we look at a special class of problems in a set of linear equations, a slightly different class of problems in which we have the equations of this form a x equal to b, but the right hand side of this equation is 0. So, in that case such situation arises, for example, when you want to find the eigenvalues and eigenvectors of a matrix A. Right. So, in that situation we have to solve equations of the form A minus lambda I x equal to 0. Okay. So, this is a set of linear equations again. Okay. So, matrix is A minus lambda I, where I being a unit matrix and A is the desired matrix whose eigenvalues we need to find out. So, the eigenvalues and eigenfunctions of this matrix is what we want to find out. So, then we have an eigenvalue equation of this form A minus lambda I into x equal to 0. And we know that such equations have non-trivial solutions, that is non-trivial in the sense a trivial solution being x equal to 0, non-trivial solutions if the determinant of A minus lambda I vanishes. So, that is the condition we use to determine the eigenvalues lambda. Okay. So, there are situations in which A x equal to b kind of equations has to be solved for matrix, okay, which can have non-trivial solutions, that is solutions different from x equal to 0, provided the determinant of A equal to 0. So, that is the kind of thing which we want to look at. Okay. So, we would say that we have an equation, matrix equation of this form, right, it's A11 minus lambda x1, A12 A1n and A21 A22 minus lambda x2, etc., and that equal to 0. So, that is the equation which we want to solve, set of equation which we just saw in the matrix form here. Right. So, then we normally what we do is, if you have an equation of this form, right, we just saw that we could find the inverse of this matrix, right, and then multiply the inverse by b, or multiply b by inverse, and then we got the x solution. That would not work here because the right hand side is 0, but when the inverse itself does not exist, that is when determinant of this is 0, we can still find a set of equations which are a set of solutions for this x, okay, which are non-trivial. Okay. So, that is what we want to find out. Okay. But constructing the determinant, right, so determinant of A lambda equal to 0, that is what we want to find. The constructing the determinant itself turns out to be non-trivial when A is very large. Right. So, we assume that the determinant A minus lambda I, the determinant of A minus lambda I can be expanded in terms of lambda in a polynomial of this form, okay, and we equate that to 0. So, as I said, what we want to do is to find out the values of lambda such that so we want to find out the values of lambda such that this determinant is 0, right, that's our aim. Right. So, such equations, okay, that is polynomial equations of this form, okay, that is when you expand this thing, we get this polynomial equation of this form, and now we need to solve this such polynomial equations. Okay. So, that is a discussion which we are going to have today. Okay. How to solve, how to arrive at such equations, and then how to solve. Okay. As I said, there are two problems. The first thing is to actually arrive at such equations, right. So, if you have a large matrix, then converting the determinant into a polynomial of this form itself could be a large exercise. Okay. So, first we will look at how to arrive at or how to construct this polynomial equation from this condition that the determinant of A minus lambda I equal to 0. So, that was the first discussion we would have today. Okay. So, that is what I just summarized here. So, for large matrices, constructing this polynomial itself is a non-trivial exercise. Okay. Once we have this polynomial, we can use one of the root finding algorithms to determine the solutions. Right. So, we have not discussed the root finding as a general problem, but we will look at that in the specific case of eigenvalue problems. Okay, so now we will look at one of these methods to construct this polynomial, which is called the Faddeev-Leverrier method. Okay. So that's the most this is one of the easiest ways of constructing the characteristic polynomial, that is this polynomial which determines the eigenvalues. So one of the easiest way to do the construction of this polynomial is using what's called the Faddeev-Leverrier method. We will not go into the detailed derivation or the logistics behind the Faddeev-Leverrier method. We just see how such thing can be implemented and what is that method, what is the algorithm, and how this can be implemented, and we will just see a particular case where this has been implemented. So the idea is the following. So we want to determine this equation, that is a minus lambda I into x equal to 0, and we want to find the determinant of a minus lambda I, and we want to write it in this particular form. Okay, so now this is a polynomial in lambda. Okay, so if you have an nth order matrix, okay, then we will have the order of this polynomial will also be n. Okay, we have a 4 by 4 matrix. The highest coefficient, the highest power of lambda should be 4, right? So we know that. And then these are the coefficients of those powers. That is, so you have Pn minus 1, P1, P0 as the coefficients of this polynomial. Okay, so this polynomial coefficients will now be functions of the elements of this matrix A. So our idea is to actually determine this polynomial coefficients. The fact that this equation, the determinant of A minus lambda I equal to 0, the determinant of this particular matrix, that is matrix A minus lambda times an identity matrix equal to 0, can be written in this form is I am sure is obvious to all of us. So now the question is a good algorithm to determine what is a good algorithm to determine these coefficients Pn minus 1 to P0. The first coefficient will always be 1. The coefficient of the highest power, this lambda will always be 1. Okay, so that's, or we can always write it in this form, let us say. Okay, so now we want to construct this thing. Okay, so what we do is we generate a sequence of matrices whose trace would be the coefficient of this matrix P n minus 1 to P0. Okay, so that's a Faddeev-Leverrier method. Okay, so we will generate a sequence of matrices called B, okay, and then if you have n, okay, we will have B n minus 1 to B0. Okay, so that's what we are going to have, many matrices. So and the trace of this matrix, okay, would be the coefficient of this particular order. So for example, this one, the coefficient of the first the next term, the second term in this polynomial, that is the coefficient of lambda to the power n minus 1 term, that is P n minus 1, is simply the trace of this matrix A. Now and then so that's where we start with. Okay, so this particular coefficient is a trace of this matrix. Okay, you can prove this. Okay, you can prove this using the Cayley-Hamilton theorem. That is that all characteristic equations, all matrices satisfy its own characteristic equation. So that's what we can use to prove this. Okay, but we don't go into the proof. We are looking here only at the algorithm. So we say that the first coefficient, that is the coefficient of lambda to the power n minus 1 term. So lambda to the power n terms coefficient is 1. Okay, and the coefficient of the lambda to the power n minus 1 term, and that is the trace of the matrix A. Okay, so first matrix B, that B n minus 1 here, okay, is just the trace, is the matrix itself, A itself, okay, and we take the trace of that. Now other coefficients are determined through a series of recursion relations of this form. That is now the next one will be B n minus 1 we just saw. Okay, now B n minus 1 is A itself. Now B n minus 2 is then constructed, or B n minus I in general is constructed from B n minus I plus 1 by this relation. Okay, so we started with B n minus 1, which is A itself. Now we take B n minus 2, that is I equal to 2, and that's equal to the matrix A multiplied by b n minus 1. Now, I is 2. So, n minus I plus 1 is 1, n minus 1. So, it is b n minus 1, which was matrix A itself, you remember. Now, minus the coefficient which we just now got, that is p n minus 1 multiplied by the identity matrix. So, that is how we construct these matrices b n minus 1s, b n's. Okay. Then we take the trace of that matrix, okay, divided by the I. Okay. So, in this case p n minus 2 we want to construct, right. So, I is 2. So, it is 1 by 2 times the trace of b n minus 2. Okay. So, then we can continue this. So, this is a recursion relation. So, once we have the b n minus 2, we can go back here, right, and we have the p n minus 2 and the b n minus 2. The trace, you remember, is just the sum of the diagonal elements of the matrix. So, sum of the diagonal elements is a trace. So, trace of b is b I summed over I. So, once we have the p n minus 1 and then we go back here, okay. So, we have now p n minus 1 and p n minus 2, then we can construct b n minus 3. So, b n minus 3 is now matrix A times b n minus 2 minus p n minus 2 into I, the identity matrix. Okay. Now, we need to go till I reaches n, that is until we get b 0. Okay. Now, the b 0 finally we get, and the reason that b 0 will be then since now n minus I is 0, b 0 would be matrix A into b 1 minus p 1 of I. Now, there is an interesting, so that then p 0 then is 1 by n times, right, then n, I is n now. So, 1 by n times the trace of b 0. So, I repeat, so we start with matrix B n minus 1, we will take that as A. Right. So, the trace of this, that is the sum of the diagonal elements of this matrix, that is the sum of the diagonal elements of the matrix A itself, is the coefficient of the lambda to the power n minus 1 term, and then we continue, right, and then we use first we start with b n minus 1 as A, and then we construct all b n minus i's using this recursion relation, that is A into b n minus I plus 1 minus p n minus I plus 1 into lambda into I. Okay, so, now you could substitute this back into the equation and see that the matrix A satisfies the characteristic equation, something which I said we will not go into, but it comes from this equations come from the Cayley-Hamilton theorem. Okay, so, now we have p n minus 1, that is the trace of this, okay, and once we have the p n minus I, okay, we can go and construct the next p n minus I, etc. Okay, so, we continue this till we reach the value b 0, and once we have b 0, and that is A into b 1 minus p 1, and then we have all the coefficients. We have p 0 then, and we have all the coefficients. Now, there is an interesting fallout of this, that is the fact that A inverse. Okay, so, now we just saw that here, that b 0 is A into b 1 minus p 1 times I. Right, that is what we just now saw, and the b 0 is a trace of this, and from this equation we can construct that A inverse, right. So, we will turn out, we will find that the A inverse is then simply related to 1 by p 0 b 1 minus p 1 into I, because we just saw that we can construct b 0 and the trace of that, okay, is just p 0. So, if you take the A inverse of that, so if I divide the right hand side by 1 by p 0, then I should be just getting an identity matrix, right. So, I will get A inverse then as 1 by p 0 b 1 minus p 1 of I. We will just see this in an example, we actually implement this and then see this, we will see all the details of how we get a much more better feeling of how we actually arrive at this. So, as I said, a complete explanation of this is beyond the scope of this course, okay, but we could see this from this whole idea comes from the Cayley-Hamilton theorem. If you are interested, and you could look at just the Cayley-Hamilton theorem. Okay, so, now we just look at an example. Okay, so, we will for example have a matrix of this form 2 minus 1 0 0 and minus 1 2 minus 1 0 and 0 minus 1 2 minus 1 0 0 minus 1 2. So, that is our matrix. Now, we want to construct the eigenvalues of this matrix. So, So, we take such a 4 by 4 matrix because you can actually do this by hand, okay. But the idea is that this programs of this type can easily be scaled to a large matrix n. So, we will start with this. So, as I said that we will have b n minus 1 as set equal to a. Okay. So, we will also see a program in which this is implemented, and we will compare, we will go step by step in this. So, here is a program which basically implements this. So, I have a matrix D, right. So, I have the usual thing which we have been doing for all the set of linear equations problem, that we have a matrix D, right, and we have the elements of this matrix as now, as I said, I just put in exactly the same as we just see on that. That is, when you print this out, it will be exactly the same as this matrix we have 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2. Okay, so we have this matrix. Now I just store this matrix before I do anything to this matrix. I just store this in another variable C. So, because I am going to pass this matrix D into a function called eigenvalue, that is E value, and that this function which takes in, to which I pass D, will return the eigenvalues in an array Y. Okay, that is the idea. So, Y is an array, is a one dimensional array. So, I have a 4 by 4 matrix, and the eigenvalues will come out in a one dimensional array Y. And since this program might alter, this program actually alters my matrix D, I store that in a matrix C before I pass it on to this. This is just for comparison, it may not be required in an original program, in an actual program. Okay, and then, so what I do is, this is the main program here, it's very simple. The main program basically just defines matrix D and stores the whole elements of that in a matrix C, and calls this eigenvalue function and exits. That is all it does. Okay. So, we can do further things with this eigenvalue equation. Sorry, yeah, this will just, y is not the eigenvalues, I am sorry, y just gives you the coefficients of the characteristic polynomial. So, this particular function will just simply return y as the coefficients of the characteristic polynomial, and then the main program ends. So, the main program ends here. Okay. So, the main program ends here, it just calls the function to which it passes D, and it gets back the coefficients of the characteristic polynomial in this metric, in this one dimensional array Y, and n is the order of the matrix. Okay. Order of the matrix minus 1 in this case, because it starts from 0. Okay, so it goes from 0 to 3, n is 3 in this particular case. Okay, so I have defined n as 3 here, right. Okay, so that's all it does. Okay, so now this program doesn't do anything more, because we would want to append this program with the solution of the characteristic polynomial later. So right now we just determine the characteristic polynomial itself. Okay, and then we go there. So now this is a function which does the calculation of the characteristic polynomial. So to which, so now this function receives the matrix D as a 2-dimensional array of pointers. So here is another example in which you pass a 2-dimensional array as to a function, and the function receives it as a 2-dimensional array of pointers. We have seen this in the earlier lecture, the passing an array into a function and the function receiving it as a 2-dimensional array of pointers. So here that example of that. So it receives, this function receives it as a 2-dimensional array of pointers. You can also receive it as a 2-dimensional array itself. I use this just to show you how to use, how to implement this kind of passing 2-dimensional arrays. Okay, and now this receives, it receives a 1-dimensional array just simply as an array of dimension 4, and then it receives the order of the matrix as an integer. So now I have another set of integers defined here, and then I have another matrix defined here, and okay, there is an identity matrix, and then there is a matrix S, which are all working arrays which we would require as we go along. We will see that. Okay. And then this function calls another function, and so there is a function pointer here. This is a function, this is another function, and that is called multiply. Okay. So, this function is basically is to multiply two matrices. Okay. So, this is just this function's idea is to multiply it, give two matrices and it multiplies it, we will see that. Okay. And there is another function here which simply calculates minus 1 to something to the power n. Okay. So, now it receives, as I said, the matrix D, right, and then I just print that out matrix D such that we see that it has received it correctly, this function. Okay. So, let us just pass it on to this function and just print that out. Okay. So, first thing maybe we should just see that it actually receives it correctly. So, okay, so now that is the first part here. So, that it received, ignore all this. So, first part here that it has received the matrix, okay, everything as a floating point number. Okay, so, everything is a floating point number. So, you can see 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 2. It is the same thing which you have just written down. Okay, so, then what we do then is to the matrix S. So, now we have to construct, our idea is to construct this matrix as B's, okay, which I call S here. Okay. So, the first order, the first matrix is simply the matrix D itself, right. So, that is what I am doing here. Okay. So, in this loop that M goes from 0 to n, as I said, now it goes from 0 to n, that is the order of the matrix, n is 3. So, the order of the matrix is 4 and J goes from 0 to n, and then we have this matrix S is simply the same as matrix D. That is what B n minus 1 was, remember, is the matrix D itself, right. So, this is B n minus 1 now, the S, that is matrix D itself. I also use this array to define my identity matrix. Right now, the identity matrix, I define this matrix I with all the elements 0. That is what we have now. So, I just define a matrix here which is all the elements 0. We will see the use of this right in a little while. So, here is this matrix B n minus 1, which is just the D itself, right. So, and then what we want to do, we want to compute the trace of that matrix. Okay. So, there is a whole loop here. Okay. So, what I did is first, before I enter the loop, I just define my B n minus 1 as D itself, okay. And then I will now go for I, right. So, now we have, remember, this recursion relation. So, we will have to use this recursion relation, right. So, but B for I equal to 1, that is B n minus 1 is simply A. So, I could define that outside, and then I get into this loop which would which uses this recursion relation to determine the B n minus 2, n minus 3 and n minus 4, or in our case it will be just up to n minus 3 because n is 3. Okay. So, I will start with B n minus 1. So, that is the first quantity which is the D here. Yeah. So, which is the matrix D here. So, that is the first quantity. And then I come here inside this loop. Okay, now this is actually entering the recursion relation. So, first I do is compute P n minus 1, that is a trace of this matrix A or the D here. Okay. So, remember the matrix D is the A in the nodes, and S is the B in the nodes. Okay. So, now I use this S, I compute the trace of that. So, I define x equal to 0 here and then sum all these quantities, right. So, I sum all the diagonal elements J J. So, all the diagonal elements of this matrix S is summed here, okay, and that sum, so this loop ends here. Okay. As you can see, this is simply a loop which ends here, right. Okay. So, that's for all the J values. Okay. So, I summed over all the diagonal elements of x. So, that gives me P n minus 1, right. That P n minus 1 is determined, or the coefficient of the lambda to the power of n minus 1 term is now determined here, okay, as first term, and there is nothing to divide that because that is I is 1. So, P n minus 1 by 1 is P n minus 1. Sorry, that the trace divided by 1 is just the trace itself, right. So, P n minus 1 is simply the trace of this matrix D. Right. So, that is what we have done here. Right. So, we just computed the trace of the matrix B n minus 1. Okay, so that's what the first step is. Okay, so that is what we should get, and then so and then we will go on constructing other elements. First, we look at the trace of that quantity. Okay, so that's been computed here. So you can see it's 2, 2, 2, 2. So the trace of that. Okay, so now for n, now it's n is 3. Okay, here. So I was 1. So n minus I is 3. So order is 4, so order minus 1. So this is the coefficient of the lambda to the power 3 term. That is what this 3 signifies here. Okay, so it's a 4th order matrix, 4 by 4 matrix. So the coefficient of the lambda to the power 4 term is 1, and this is the coefficient of the lambda to the power 3 term. Okay, and that's the trace of this matrix, which is 8, and that's what I have written here. So that's a trace, and this is a trace by I. That's both 8. So I'm printing out the matrix. It's the order of the term which I am looking at, the trace and the trace divided by I. Okay, so then once we have done that, now we go back and then look at the next matrix, right. So that is trace we got now. So we will just write that down here as a trace of the B3, as B3 is A and the trace of that is 8. Okay, so that's a term which we just write it down. Okay, now next step is to construct this matrix, right, is A into whatever the Bn minus 1 we had here minus the P3 which we obtained here multiplied by the identity matrix. Okay. Basically, we have to do this calculation here. That is, we have to subtract P3 minus I and multiply matrix A, okay, or multiply matrix A and A, that Bn minus 1, Bn minus 1 is A, and then multiply this matrix with this matrix, identity matrix multiplied by P3 and subtract. Okay, and that is a new matrix Bn minus 2, n being 4, it will be B2. That is what we see here. So the B2 should be given by this. Then, and that is implemented here in this form. Okay, so I have, so I am trying to also use the elements which we learned in programming here. Okay, so we have just constructed the trace of this matrix, right, and which will be divided by n minus k plus 1 is the I. Okay, that is the 1 right now. Okay, and I just printed that out. You saw that it has been printed out. And now we go into if k is greater than or equal to 1, that is in this case. Okay, then we will go here. Okay, and then we will next multiply the matrices D and S. So here is a subroutine, as a function to which we pass the matrix, two matrices D and S, does not matter what matrices, two matrices D and S and its order. Okay, two matrices of the same order and the order of the matrix, we just pass that, and this function returns a product. Okay, so that is what this particular function is doing. Okay, so again notice that I pass two functions, two matrices, two arrays, two-dimensional arrays. In fact, this is a two-dimensional array of pointers right now, and then a two-dimensional array. I just pass these two, and then I get return. What I get is another matrix C. Okay, so how do we do that? So this will be a function which has to return a two-dimensional array. So this uses both the things we learned in the lecture 4, that is how to pass a two-dimensional array to a function and how to get a two-dimensional array back from that function. Okay, so both are here. Right. So now this has to be a two-dimensional array, so it has to be declared appropriately. So that is what we have done here. Okay, now this is been declared as a two-dimensional array of pointers C. Okay, so C will be our product. Okay, the product will come out as C, and that is a two-dimensional array of pointers of dimension 4 by 4, and this multiply, this function has to return that two-dimensional array. So that also has to be dimensioned, be defined appropriately, and that is returning a floating point number. So its float, its type is float, and it is an array, two-dimensional array. So it has, and its dimensions are 4 by 4. So this is a way to define a function which returns a two-dimensional array. Okay, so please note that we have gone through this earlier, but I am just showing you an implementation or a use of that routine here. Okay, so I just pass this matrices D and S to this function, okay, and it returns a two-dimensional array. So we are basically doing this multiplication here. So we are doing the multiplication of the matrix D and S. Okay, that's what we are looking at. So that is this part. Okay, so we had constructed B3 and now we are looking at B3 minus B3 into I minus A. So first I am doing A into B3. Okay, that's what A into S, because remember S was storing this B3. Okay, so that is what's done here, and we get that product. Okay, then I store that product into the new S now. So now B3 is being now replaced by the product of the D and S, that is matrix D and B3. Okay, that has been replaced by the product. Okay, the S was the B3 matrix, remember, and that has been now replaced by the product. So I am just equating all the elements to the elements of matrix C. So the elements of matrix C, being a two-dimensional array of pointers, is read out like that, as in brackets an asterisk C and Mj. Mj are the elements, and so that this gives the matrix S the values of this, or this points to the value of the mjth element of the matrix C. Right. So that has been, so we are equating that to S. So S was B3 to start with in this loop. So now S gets a new value, that is D into S. So now we have to construct the second product, that is we need to construct P3 into I. Okay, so that has been done here. Okay, so then I go again and then do the product D and I, that is matrix A and I, the identity matrix. Right, the identity matrix, now remember it was identity matrix to start with. Okay, so now the idea is that all the diagonal elements of the identity matrix are now replaced by the y of k. Okay, so now y of k, you remember, was the P3, right? Okay, so I have replaced the y of k, so that is P3. K is 3 here. Okay, so remember we start with k equal to n, so k was 3. Okay, so now P3 is now in the y of 3. Okay, so now that is P3 into I, right, is now simply replacing the diagonal elements of this matrix by that element. Remember a constant into a matrix, an identity matrix. So the diagonal elements goes into the value P3. Okay, then I subtract these matrices. Okay, these two matrices are subtracted. That is, this is the product of D and B3, and this is the product of, now just saw, so D and identity matrix multiplied by P3. So we subtract and then we have the matrix B2. Okay, now this looks tedious here, but once we have written this one round and then the rest of the things follows, right. So that is now the same thing. So we have constructed B2 and now we go back. Once we have done that matrix B2, we just print out the matrix B2. Okay. That is what I wanted to do here. So I just print out the matrix B2 here, okay, and you can see that as the matrix I just print out. So that is 11, 4, 1, 0, 4, minus 10, 4, 1, 1, 4, minus 10, 4, and 1, 4, minus 11. Okay. So that's a matrix B2 which we have got. Then we have to compute the trace of this. The trace of this is 42. Okay, that's a trace. That's what we put it here. So n minus 2 it is. So this Pn minus 2, and so the Pn minus 2, and then once we have constructed this matrix, we are simply going back from here. This loop ends here. Okay, so we go back here, right? We go back here in this loop, okay, into the k loop, and we will, yeah. So we are going back here into this loop. Okay, after we print out this matrix, the B2 matrix, now B3 has gone to B2. All S is now replaced by B2. Okay, it was B3 before, now it will become B2, and then we go back. This loop ends here and it goes back here and computes the trace. Okay. Now once you have the trace, now we have to divide it by n minus k by plus 1. That will be now 2. Okay, so now we have to divide it by 2 because our I in this program is 2. Okay, so the P2 is the trace of B2 divided by 2. So that is what you are going to get here. Okay, so that will be that is what has been printed out here. So that will be, the trace is 42 and divided by 2, that is 21. So the next coefficient is 21. Okay, and then we can repeat this process, and we can will continue to now construct B1. Okay, B1 will be again the product minus P, now P2 into I. Now P2 is 21, so P2 into I, okay, and then we keep doing this, okay, till we get all the coefficients in this form. Okay, that's what we are going to do, and we will get all the coefficients here. Okay. So that is what this program does. So the program simply repeats this loop till we reach B0, okay, and we will construct all the coefficients one by one. Okay. So that is what we will be doing. Okay. So we have coefficients 21, and then we have 20, and then we will have 5, okay, and that is where it ends. Right. Now notice that one more point, when we reach B0, right. So when we reach B0, we have all the diagonal elements as -5, okay, and everything else is 0, right. So we can see that the B0 matrix divided by P0 is an identity matrix. So that is what I said, we will use this, that is what I was telling you, that we can use the last coefficient, that when it reaches B0, okay, which is simply B1 minus P1 into A, that was B0, right, that B1 minus P1I into A, that is B0. Now we saw that B0 divided by P0 is an identity matrix, right. So that means what? That means B1 minus P1I is, so if I B1 minus P1I divided by P0 is the inverse of A, because if this has to be identity matrix, this has to be the inverse of A, right. So we can see that A B1 minus P1I by P0 is the inverse of A. So this process can also be used to compute the inverse of the matrix, inverse of a matrix of this form. Okay, so we can construct that too. Inverse of the matrix A we constructed not by using adjoint A by determinant A, but by using this technique of Fadev and Leverrier. Okay, so that is what we have seen here. Okay, so now we have the characteristic polynomial, and the coefficients lambda for has 1, 8, minus 21, 20, and minus 5. Okay, so we have this coefficients, we have the polynomial, and now what we have to do is to just go ahead and solve it. Okay, now that is also a non-trivial exercise, because if the n is very large, we will have a very large polynomial, and then we have to find out all the roots of this polynomial. So if n is the order of the polynomial, we will have n roots, and we have to determine all the roots. So now we will use one technique here, that is, if all the coefficients of this polynomial are real numbers, then the roots has to come either as the roots should be either real or pairs of complex conjugates. Okay, that's what we are going to use. We are going to use that, and we only look at that special case where we have all the coefficients of this polynomial as real. Okay. So and we will try to solve this equation by using what's called the Barstools method. Okay, that's what the second part of the polynomial of the eigenvalue determination, which we will be looking at now. Okay, so now we saw that typical polynomial can be written in this form. We know that, right? A typical polynomial can be written as fn of x as a0 x plus a1x up to an of x. Okay. We were looking at the case where x was our eigenvalues, which we call lambda, and this was the coefficients we call as p's, etc. Okay, so that's the same equation here. Okay, so now we know that the roots come as pairs. Okay. So since we know the roots comes as pairs, and pairs of because the coefficients are real, then the root comes as pairs of complex conjugates, or always they will come in pairs. Okay, so we can make use of that, and we say that the polynomial, since the root comes in pairs, okay, the polynomial should be always divisible by a quadratic polynomial of this type, x squared minus rx minus s. So what we are saying is, we take this polynomial, we want to find all the roots of this polynomial, but we know the roots comes in pairs. Okay, so I can say that this polynomial should be divisible by a quadratic polynomial. So I construct a quadratic polynomial of this form, x squared minus rx minus s. I construct this quadratic polynomial. I divide my original polynomial fn, order n polynomial, by this, and then I will get a polynomial of order n minus 2, right. And if I just take an arbitrary quadratic polynomial of this form with some coefficients r and s, and if I divide my polynomial of order n by that, okay, I will get a polynomial of order n minus 2, and I will get a remainder, okay, which is b1 into x minus r plus b0, a first order remainder. So that is what would remain. Okay, so you have a polynomial and a remainder, and then what we need to do is determine this b1, bn minus 1 up to b2, right, and then b1 and b0 would be in the remainder. So now this is an exact divisor, okay, that is, if x squared minus rx by nsh, this quadratic polynomial is an exact divisor of the nth order polynomial which we had, and then this part would be 0, this r would be 0, right. Okay, so the r will be 0. So what we have to do is determine this r and s such that there is no remainders left, right. So we need this b1 b0 to go to 0. Okay, so we have to choose r and s such that b1 b0 is 0. So that is the whole idea behind Barstools method. So and because we know how to construct this polynomial, if you know the coefficients of this polynomial, okay, that is a's, which are original polynomial coefficients are written as a's. If you know all the coefficients of this polynomial, and then if I choose an r and s, okay, I know what the values of b1, bn minus 1 and b2 are. Okay, I can write down this equation for this. Okay, and I can also get b1 and b0 from that, and then I can make sure I can tune my r and s such that this goes to 0. So that's what we are going to do. Okay, so here is a simple recursion relation for again for that coefficients. So we have bn's as the an, okay, bn minus 1 as an minus 1 plus r bn, and bi in general as ai plus r bi plus 1 plus s bi plus 2. Okay, so now remember what bn's are. Bn's are the coefficients of the polynomial which you obtained after dividing the original polynomial by the quadratic polynomial. That is, we will go back again and then please take note of this. That is, we had this polynomial which had a0 as a coefficient of the x0 term and a1 as a coefficient of x to the power 1 term, a2 as a coefficient of x to the power 2 term, or in general an was the coefficient of x to the power n term, right. And then we divide this by a quadratic polynomial, and then we had bn as a coefficient of the n minus 2 power term. Okay. So that is what, please note that. Now we have written our notation is that bn is now the coefficient of the n minus 2 power term. Now we will divide this further. Okay, now we will choose this as our original polynomial. This will become an minus etc. minus 2 an minus 1 etc. and then divide again by quadratic, and then this becomes the coefficient of the x, the highest power become n minus 4. We will continue with that way. So the notation is that bn is now the coefficient of the xn minus 2 term. So once we have one loop, and then we can just continue the loop and determine all the coefficient, all the roots, right. So okay, so that's what we are writing here. So we are writing the bn is equal to an, that is the coefficient of the x to the power n term is the same as the coefficient of the x to the power of n minus term obtained after dividing the nth order polynomial by a quadratic polynomial, and the n minus 1 term, which is the coefficient of the n minus 3 term, that is bn minus 1, is a coefficient of the x to the power of n minus 3 term in the polynomial obtained after dividing. That polynomial, that is equal to an minus 1 plus r times bn, where r, remember again, is the coefficient of the linear term which we use to divide of the quadratic polynomial we use to divide the polynomial. Okay. So please note down all of this. Okay, and then you have so now we can construct this series of b's from that. So for example, b is, let's say we have an nth order polynomial, we have n equal to 4, so b4 is a4, b3 is a3 plus r times b4 etc. And we can keep on, and then n minus 2 onwards will start, we use this equation. For n and n minus 1 we will use this, if n minus 2 onwards we will use this equation. Okay, so again, so we assume that the solutions comes as complex conjugate pairs. So the solution would be obtained now by just simply, so what we done at the end? At the end we write the polynomial fn order n as polynomial fn minus 2 multiplied by x squared minus rx minus s, right, and that is equal to 0. So, the solution will be obtained by saying x squared minus rx minus s equal to 0, and we know how to solve this quadratic equation. So, we get 2 roots. Okay. So, we got 2 solutions to the nth order polynomial equal to 0. So, we took the nth order polynomial, we factorized it as an n minus 2 order polynomial and a quadratic polynomial. So, we have polynomial of order n multiplied by a quadratic polynomial equal to 0, and then we say that the quadratic polynomial, the term is equal to 0, okay, and that gives us a solution, the 2 roots, okay, and we can continue this till this polynomial becomes order 1 or order 2, depending upon the original polynomial was even or odd. Okay, so that is what we have. Okay, we will get more idea of this when we actually implement this in a code. So, we have all the roots. Okay, so now once we have the roots, okay, so we have the bn's. Okay, so now what we are saying is that if this is an exact divisor, right, then the remainder, that is b1 x minus r plus b0 should be 0. So, we just choose an arbitrary r and s, divided the nth order polynomial, and we got an n minus 2th order polynomial with the coefficients as bn2, b2, and we got a remainder which is b1 and b0. Right. But if this is an exact divisor, the remainder is 0. Okay. So, we have to choose r and s such that b1 and b0 are 0. Here again we will go back to the kind of iterative scheme which we had used in the case of fitting a nonlinear equation, fitting a nonlinear function to a set of data points. So, we will use the same techniques here. So, that is we will say that b1 of r plus delta r, so that b1 and b2 should be equal to 0. Okay. So, now what we do is we will expand this polynomial. Okay. So, we will expand this polynomial in using a Taylor series, okay, and then we will write b1 we will expand this coefficient b0 and b1, which should be 1, which should be actually 0 if this is an exact divisor, but we choose an arbitrary r and s value, they will not be 0. Right. So, but then we say that our choice is near perfect, okay, or almost correct. Okay. So, we are very close to b1 and b0, or b1 or b0 will be small. Okay. So, then I would do is I would expand b1 and b0 around the r and s value we chosen, okay, and get a new b1 and b0. Okay. So, the new b1 and b0, that is a new b1 and b0 close to r and s which you have chosen is r plus delta r and s plus delta s. Can be written as b1 plus del b1 by del r and delta r, del b1 by del s into delta s, and similarly for b0. So, remember the idea here is that if you are choosing the correct r and s, b1 and b0 should be 0, okay. But if they are not 0, I should be able to go around the values I chosen r and s, okay, such that I go to b1 and b0 equal to 0. So, that is what I am trying to do here. So, I am just going around that. So, I am changing r by delta r and s by delta s. So, the new values are r plus delta r and s plus delta s. And what is my new b1 value there, and that is given by this, the Taylor expansion, and what is my new b0 value there, and that is given by this Taylor expansion. Okay. So, if the delta r and delta s is correctly chosen, the left hand side should go to 0. Okay. That means I have an equation that b1 plus del b1 by del r into delta r, del b1 by del s into delta s equal to 0. Okay. So, then that is what I would have. Okay. So, I have this equation. And then I can solve this equation, because del b1 by del r, if I can determine del b1 by del r and del b1 by del s and del b0 by del r and del b0 by del s, okay, I can determine the new delta r and delta s values, and I can go to new values of r and s. Okay, that is the idea. Right. And I can determine this because I know how to write that, right, because I know how the b's depend on r and s. Okay. I have that equation. Okay. Since I have that equation, I can determine how. Okay. I know how this coefficients, for example, depend on r and s. Okay. So, I saw for b1 will be a0 plus r b2 plus s b3. right. So, del B1 by del R will be B2 and del B1 by del S is B3. And similarly, del B0 by del R will be B1 and del B0 by del S should be B2, and that is what I can use. So, I can use that and substitute that here in this equation, okay, and then I can get a set of linear equations, okay, and I can solve that. Okay. So, I have these equations, okay, and then I can just write that down here. Okay. So, I have written that for a special case of where this is equal to 0, and then I can use these equations and differentiate this with respect to R and S, and I can get this coefficients here. So, since they are coefficients of this polynomial, I will call them C's, okay, but then I can determine that coefficients from this recursion relation which we had, and then I can get the left hand side. I can then solve this equation for delta R and delta S, okay, because I know B1 and B0. So, that is the idea. Okay, so, then we will get a new delta R and delta S, okay, and then we could compare what is the delta R and delta S now we obtained, okay, relative to the old R. So, new R will be R plus delta R, and the old R will be new S will be S plus delta S. So, the relative error in one iteration step would be delta R by the R into 100, of course. So, percentage error, and then we could put in some tolerance for this, okay, and when it goes below some value we would stop. And then that way we can produce all the coefficients. So, we can get the solutions R and S. So, when we have the coefficients or the quadratic equation, so we have then x minus Rs plus x minus Rx plus S equal to 0 as an equation, and then from that we can determine the two roots. And then we have an n minus 2 order polynomial left, right, and that n minus 2 order polynomial we can again divide by another quadratic polynomial. Right, and then we will go to an n minus 4 order polynomial into a quadratic polynomial, and then from there we again get two roots. So, we can continue this till we determine all the roots. Okay, so, once we have done one loop, there are three possibilities left. That the quotient is a third order polynomial. So, that is, if you started with, we continue this loop, right, finally we end up with this, that the last thing would be that we will reach a third order polynomial if you started with an odd number, then we will end up with a third order polynomial. So, we can do it one more round and then get the values of R and S for that. Now, the quotient is quadratic. Okay. So, if you start with an even order polynomial, and then we will end up with a quadratic equation, okay, and then we do not need to divide that further, right. So, then we have, that means the last equation we get is a product of two quadratic equations, and we can easily determine the roots, all the roots. Now, the quotient is a first order polynomial, that is one of this can occur, right. We will end up in a third order or a first order polynomial, and then the remaining single root is simply x equal to minus S over R. So, in the case of the fourth order polynomial which we were discussing, we just need one division, right, because once we divide it one round, okay, so we have only a quadratic polynomial left, okay, and then that means we write the fourth order, if you use Barstools method, and we have this fourth order polynomial which we are discussing, we can write that as the product of two quadratic polynomials, okay, and we have all the solutions left, and that is something which we will be looking at, right. We will implement that in a code, and we will actually evaluate those coefficients. This is not the only way of determining the eigenvalues. There are other methods of determining the eigenvalues also, okay, and eigenfunctions also. So, we will discuss some of those methods briefly, not in so much detail, and briefly we will for example, we will see what is called the power method for determining eigenvalues and eigenfunctions. And this method actually uses the fact that the eigenvectors form what is called a complete basis. That is, if you have a matrix and if you know all the eigenvectors of the matrix, okay, they form a complete basis. That is, any other vector we can express, okay, in terms as a linear combination of these vectors. Okay, now, each of this x1, x2, xn I am mentioning here for an nth order matrix is a vector by itself. They are column vectors. X1 is a column vector, x2 is a column vector, etc., and they form a complete basis, okay, with eigenvalues lambda 1, lambda 2, lambda 3, etc. That is, if you given any arbitrary vector v, okay, I can write that as a combination, linear combination of these set of matrices, this set of column vectors x1, x2, x3, xn. And and now if you take a matrix and multiply the matrix, desired matrix A, and multiply this vector by that, okay, and then we will get we can get an equation like this. It's a new vector v1 would be matrix A times v0 plus a1 into, because we have expressed v0 as a1 x1 plus a2 x2 a3 up to a n xn. Right. So when you multiply it by A, then you will get an equation of this form. But we know that x1, x2, x3 are eigenvectors of the matrix A. That means ax1 I can write as lambda 1 x1, and ax2 I can write as lambda 2 x2, etc. So I will get an equation of this form on the right hand side. So I had an arbitrary vector v naught, which was expressed in terms of the eigenvectors. Okay. Then I multiplied that by the matrix A, whose eigenvector which we want to find, and we got a matrix of this form. So now what we see is that if you repeatedly multiply this matrix, okay, this vector by this matrix A, okay, and then we will go to lambda to the power n, lambda 2 to the power n, etc. And then if this lambdas are ordered correctly, okay, the only term which would be left would be the highest power lambda. So that way we can get the vector by simply taking an arbitrary vector and multiplying repeatedly by matrix A, we can get the eigenvector corresponding to the largest eigenvalue, and that is what is called the power method, and we will see the use of that or implementation of that in the next lecture.